Welcome along. Now, my name's Dr. Alan Wood, and I'm a senior lecturer in the physics team at Nottingham Trent University. Now, all universities have their own specialist areas of research, which are often done in collaboration between different institutions. And I want to tell you a little bit about some of the research work that we're involved with at Nottingham Trent University using a telescope called the International Lofar Telescope. And this work is done in collaboration with some of our colleagues around the UK and further afield as well. Okay, so if I just do a screen share, I will get the presentation we're going to have a little look at here today. Here we go. So this is about the work we're doing with the International Lofar Telescope. So first of all, why use a telescope? Why use a telescope at all to look at the night sky? Well, let's just start off with these basic reasons. First of all, increased light gathering power. If you've got a telescope with an increased area, we get more light. Objects become brighter, and so that can be a really good thing. Now, even when we go on to talk about radio wavelengths later, I'm still going to talk about increased light gathering power because it's all part and parcel of the electromagnetic spectrum. Okay, so why use a telescope? Increased light gathering power. Objects become brighter. Why else use a telescope? Increased angular resolution. Now, there's a diffraction limit to what we can see. So even if we can magnify something more and more and more and more and more, which is another key benefit of a telescope, we can put our lenses in, so we can magnify an object. Even if we can magnify it more and more and more and more, there's a point where we can magnify it no further. And that's given by this equation here, which tells us the maximum angular resolution. This is related to the diameter of the aperture and the wavelength at which we're observing. So here's a second key reason. An increased diameter gives us more detail. So there's two key reasons: increased light gathering power and increased angular resolution. There's of course increased magnification as well in an optical telescope, but we're not going to worry too much about that today. Because what we're going to think about is we're now going to think about radio wavelengths, and we're going to think about the International Lofar Telescope. Now, you might be familiar with seeing some images of telescopes such as the radio telescope at Jodrell Bank. It is huge. It's tens of meters across, and that helps us get a fairly good light gathering power. It helps it get a fairly good level of detail based on the diffraction limit. But suppose we want to see even more detail. If we build a telescope, say the size of Central and Western Europe, then we get a lot more detail based on the diffraction limits. And if we covered Central and Western Europe in a telescope of that size, we'd of course get a huge light gathering power, actually far more than we'd need. Now, covering Central and Western Europe in a massive telescope might not be a terribly popular thing to do. So we don't do that. But if instead what we do is if we have receiving stations all across Central and Western Europe, then we can get a telescope which has the light gathering power of the sum of the areas of these individual stations, but can see the level of detail as if the telescope was this big, going all the way from here to here. And what do we get with the International Lofar Telescope? Well, we can see distant radio sources. And this is what LOFAR is designed to do. It's designed to peer into the distant universe, look back at the dawn of time. And that's what loads of people on the LOFAR team are doing. That's not actually the work that we're involved with at Nottingham Trent University ourselves. We're looking at something rather different. Now, if you look at some of the distant radio sources here we can see right ascension and declination. So this is basically position in the sky. We see that under normal conditions, there's nothing really changing here, and that's what the LOFAR team would like. However, we sometimes get things like this. We can see these structures move. You can see these radio sources moving around. You can see them brightening and dimming over time. And that is because of structures in the ionosphere, the part of the Earth's upper atmosphere made up of a plasma. And that's the work we're interested in looking at Nottingham Trent University. And that's useful because it tells us about the Earth's atmosphere itself. And it's also useful from a point of view of astronomy, because if we can understand that, then we can deal with these kinds of issues here, which stop astronomers making some of the observations they would like to make. So what's happening to the radio signals coming from distant galaxies? Well, here we've got the ground, and here we've got some plasma structures in the Earth's upper atmosphere. And these plasma structures are denser than their surroundings. So if we look at radio waves coming in from a distant radio source, like a distant galaxy, Well, as they go into this dense structure, they bend towards the normal. As they come out of that structure, they bend away from the normal. And if we get the geometry right, we can see those radio waves focusing to a point. So we're going to get variations in intensity. Now, suppose these structures are moving. If these structures are moving along in the atmosphere, well, then an observer on the ground is going to see the strength of the radio signal varying too. This refraction gives us a variation in signal intensity. If these radio waves begin to interfere with each other, we'll get a diffraction pattern, and we can get some rapid variations in signal intensity, and that's a phenomenon called scintillation. Now, where do these structures come from themselves? Well, suppose you throw a rock into a pond. You can see the ripples spreading out all over the surface. Now, a disturbance in the Earth's atmosphere can cause ripples to spread out as well. Imagine there's a big thunderstorm. We can get ripples spreading out through the Earth's atmosphere because of that thunderstorm. Suppose we get something like the Northern Lights. We've got energy dumped into the Earth's upper atmosphere, up at the polar regions. Well, just like ripples in a pond, we can get structures spreading out from that. And those sorts of things can cause these kinds of structures. We don't know exactly what causes a particular event in general, but we've got a fair idea of the kinds of underlying processes like thunderstorms, like space weather, that might cause some of these in general. Of course, there's problems. What I've drawn here are these nice regular structures. The natural world doesn't work like that. These structures may not be regular. We might have different structures at different altitudes. We could have structures within structures. The natural world is a beautiful place of immense variation. So let's have a little look here at some work done by my colleague Gareth Dorian. He was looking at a distant radio source called Cygnus A, and he's looking at the intensity of that source as a function of time on the x-axis and frequency along the y-axis. And here what we've got is we have got the intensity of this structure over time, of this feature over time. And you can see suddenly here, the intensity varies dramatically. If the intensity is nice and even all the time, we get these reddish colors. These brighter colors and darker colors indicate variations. The brighter colors indicate an increase in signal intensity, the darker colors a decrease in signal intensity. So you can see these variations. Now, if we just look at what happens at one particular frequency as a function of time, we've got power on the y-axis, we've got time on the x-axis, you can see we've got a lot of variations here, but there's some underlying trends. The underlying trends we get during the course of the day, because where the radio source appears to be compared to the observer changes. We're used to things like the sun rising and setting. Well, these distant radio sources rise and set as well. We need to remove that. When we remove that, we get just the variations, and that's what we want to investigate. Now look at these variations. They arise really quickly. We can look at these at lots of different frequencies. Here we are zooming in at one particular bit of time. And you can see these variations are rising really quickly, taking about 60 seconds to reach a first peak. These spikes have a very short lifetime, tens to hundreds of seconds. And what might they be to do with? Well, we had to look to say, well, okay, we're looking at the distant radio source, and we're looking at it at an angle through the Earth's atmosphere. And the angle we're looking at does take us close to the solar terminator, the boundary between day and night. So maybe it might be something to do with that. And it might not be. That's something we're still investigating. We get variations like this, where you can see these patterns, and we can see different things going on at different frequencies. We'd expect that because we have different amounts of refraction at different frequencies. If you think about, say, if you put light into glass, you can split it up into different colors because different wavelengths of light refract by different amounts. That's what we've got going on here. Look at this. You can see a region where the signal seems to drop out completely. And just beforehand, we've got this rippling effect. We don't know what's causing that, and that's something we're investigating. Look at these beautiful arcs. We don't know what strange and wonderful combinations of conditions are causing these arcs. And look at this. Isn't this stunning, these variations in signal intensity? We don't know what's causing those either. But if we can find out where these ripples are coming from, spreading out like ripples in a pond, maybe from a thunderstorm, maybe from the Northern Lights, maybe from space weather, maybe from something completely different, that might tell us something new about coupling within the Earth's atmosphere, about circulation within the Earth's atmosphere, and we might better understand this amazing world around us. So that's where we're going to finish this short video. Thank you very much for your attention. We've got some more videos about opportunities within physics at university on this YouTube channel, and please feel free to take a look at those, and I hope you enjoy. Thank you very much for your attention and enjoy the rest of your day.